Also one application to Gauss's law. Here we have a solid sphere of radius equal to 40 centimeter. The radius r equal 40 centimeter has a total positive charge of 26 microcoulomb. So Q equals to 26 microcoulomb. Uniformly distributed throughout its volume. So here we don't have a conductor. We don't have a metallic object. We have a uniform charged object. In this case, we talk about a volume charge density. When we have a conductor, so the charge will be distributed outside. We can say we have a surface charge density. In the case of uniform charge density, like in this case, the charge will be inside the object. So we have a volume Q equals to rho times V. Okay? Okay. What we have here, we have the sphere. We have to calculate the magnitude of the electric field at the center of the sphere at a distance equal 10. So we have to find E at R equals to 0, R equals to 10 centimeter to 40 centimeter and to 60 centimeter. Okay. Let's draw a sphere. This one. And here we have the center O. Anyway, initially at this point, let's say O, first of all, part A, we have to calculate E at the point O. Second, at 10 centimeter, you know the radius of this circle equals to 40. Here we have 40 centimeter. So here we have to calculate at 10, let's say at the point A, okay, at 10 centimeter. And at 40 centimeter, let's take a point B. And at 60 centimeter, we take point C. We have to find the field as a point O, as a point A, B, and C. And here we have a uniform charged object. So in this case, we have a charge at any point inside the object. So we can say here, in the case, a general case, okay? In the case of So in the case of uniform charged object or non-conducting object, the charge will be distributed inside the object, not only on the surface. So we can say here Q equals to, so in this case, we have a volume charge density. We can say Q equals to rho times V. Okay? Now, to calculate the field, you see here the point O and A are inside the sphere. We can take a general case, the field inside the sphere. We take the formula of this field, and we can put at a radius equal to 0, we can calculate E. At the radius equal to 10 centimeter, we calculate E. And at the radius equals to 40 centimeter, we calculate E. So we can find a general calculation, a general formula of the field inside of a sphere. Okay? At any point we can find. So here, sure, we have to use by symmetric Gauss's law. We can say by symmetric we take a sphere of radius r less than capital R. Okay, I take inside the sphere to calculate the field, the general formula of the field inside the sphere. As Gaussian surface. Okay, let's we can have the sphere here at a radius equals to small r. You know, here we have delta A, and it's a positively charged. Okay, this object is positively charged, so E must be out. At this point. Here we have E. Okay. The conditions: E must be parallel to dA, E must be radial, E must be constant. We can write flux at the position I take here R less than capital R and greater than 0 at any point inside. We can say the flux equals to integral E dA equals to Qn divided by epsilon. Okay? Here the angle between E and dA equals to 0. So phi equals to E dA cosine 0 equals to Qn epsilon 0. Okay, so E is constant at any point. We get out E. So the flux equals to E A equals to Q N divided by epsilon. Okay, A is the area of Gaussian surface. You know, A equals to 4 pi r square. Okay, and Qn, here the total Q is distributed on the total charge. So here the total charge equals to Q, but I need only Qn, which is located inside the Gaussian surface. In this case, only here. So here we have Qn here. Qn. And we said that Q is a volume, we have a volume charge density, Qn equal rho Vn. Okay, so we can say in this case Qn equals rho Vn. I repeat, it's inside here. Here we have Qn. It doesn't equal Q total, okay? Equals to rho Vn. Vn is the volume of Qn. The volume of this one equals, it's a sphere, equal 4 over 3 pi r square, okay? Here, you know, we can say equals rho Vn equal 4 over 3 pi r square. We substitute the value of A and Q in the general formula of phi. We get, I want to calculate E. E equals to Qn rho 4 over 3 pi r square okay, divided by A equals to 4 pi r, no, r cube, okay? Here we have r cube. And here r square. Okay, times epsilon. We get, we can cancel 4 and 4. We get rho and also pi with pi. 4 rho r divided by 3 epsilon 0. Okay? Let's write the final formula here. We can say, in the case if r is between 0 and capital R, we have E equals to rho r divided by 3 epsilon 0. Okay? Here we can write this equation like this. or we can substitute the value of rho in terms of Q. You know that in general, Q equals to rho times V. And also Qn equals to rho times Vn. You have to know this relation. In all the cases, rho is constant. In this case, rho is constant. If you talk about the total charge equal rho times V, the total volume, and Qn equals to rho times Vn. So Q, the total charge Q, equals rho times the total volume. We can say here rho, the total volume equals to 4 over 3 pi r cube, and Qn equals to rho times 4 over 3 Vn equals to r small r cube, Vn inside the yellow sphere. So we can keep the equation E equal rho r over 3 epsilon 0, and you can write also equals to, look here, we can say rho equals to 3 Q over 4 pi r cube. We substitute this value here. We get, let's say here we have r over 3 epsilon 0, rho equal 3 Q divided by 4 pi r cube. We get 3 and 3. You know, 1 divided by 4 pi epsilon 0 equal k. We can write here k q r divided by r cube. Okay, you know that k equals 1 divided by 4 pi epsilon 0. Okay, now this is the general equation formula of E in the case of R less than capital R. We can say equals, it can be between 0 and R, okay? We can say equal. Between these 2 points, we can say E equals to K Q R divided by R cube. Okay, let's take part A. We have to calculate E, because you know 0 is inside the sphere, 0 inside the total sphere. So E0 equals to K Q times 0 divided by R cube equals to 0. Okay. Second, to calculate for the point A, B, E of the point A, you know A is between 0 and 40. Yani we can say A is between 0 and R. EA equals to K Q times R A divided by R cube. You know K equals to 8.99 times 10 power 9 times Q. We have the value of Q equals 26 times 10 power minus 6 times the distance of A equals to 0.1 equal 0.1 at 10 centimeter, 0.1 divided by R cube. You know the capital R equal 40 centimeter. We can say equal 0.4 cube. We get the value equals to 365. Okay, let's clean. We get EA equal 365 times 10 power 3 Newton per Coulomb. Okay, C, I want to calculate E at the point B. B also, we can use the same formula, okay, by putting the value of RB, because also RB is between R and 0. So we can use this one. EB equals to K. We substitute the value of K of Q RB equal 0.4, okay, divided by 0.4 cube. We get EB equals to 1.46 times 10 power 6 Newton per Coulomb. This is at the point B. So we calculated at the point the field created at the point O, at the point A, and at the point B. Now we have to calculate the field outside the sphere. We cannot use the same formula, E equal KQR divided by R cube, because it's limited between O and R. So we have to calculate another formula here. Let's erase. Now I want to calculate E at the point C. Okay, in the case where R is greater than the capital R. Okay, in this case, E at the point C, C is located at a distance equal 60 centimeter. Let's say we have C at this point. Okay, here we have C. At 60 centimeter. Okay, you know, in the case of a sphere, this object can be considered as a point charge. Okay, we can say only when you want to calculate the field outside the object of the sphere. So if we have a sphere and you want to calculate the field outside the sphere, you can consider this object as a point charge. We can consider this object, this spherical object as a point charge. I don't want to waste your time to do the calculation by using the Gauss law. In this case, you waste your time. Okay, it takes time. You can say just it's a point charge, and you know for the field of a point charge equals to kq divided by the distance square. Okay, so E as a point C equals to k q, total q, divided by rc square. So here we can say equal 8.99 times 10 power 9 times total q equals to 26 times 10 minus 6 divided by rc equal 0.6 meter square. The answer will be 649 times 10 power 3 Newton per Coulomb. Excellent. Okay, here we can add EC equals to 649 times 10 power 3 Newton per Coulomb. Look here. I want to explain something. Here, if you look the values of the field as a point O, as a point A, as a point B, as a point C. Initially, at the point O, inside the small location, we don't have a charge. So we don't have a field. So E equals to 0. Because inside this point, it's a point with a negligible charge at the point here. At the point A, only this quantity of charge will create a field. So we have a value equals to, let's say here, equals to 365,000 Newton per Coulomb. At the point B, all the charge Q will contribute to create an electric field. So the field equals to 146,1234 Newton per Coulomb. So we have, let's say, 1,460,000 Newton per Coulomb. We have a bigger value of electric field because we have more charge which contribute to create a field at the point B. All the charge will contribute. But now, when you go away far from that ball, the field will be smaller because it's inversely proportional to the distance. Okay, so we get here 649,000. The field will decrease. If you draw the distance with respect to the field, Here we have 0. If you want, we can compare here. Look, here we have x-axis and y-axis. Okay. Between 0 and capital R, this is the relation of E. Look, for excuse me, for between 0 and R, this is a relation between E and R. Here we have E, and here we have R. The relation between them, E equal KQR divided by R cube. The relation between E and R is linear, okay? So you get this relation between them. Each time you increase the value of the radius, you increase the value of E. Here you get here you get here. Finally, you get this point. Okay, between here and here, between 0 and R, the relation, let me draw well. Okay. Okay. Here we have, in this region, we have E equals to K Q R divided by R cube. The relation between E and R is linear. Okay? This is in the case where R is less than or equal capital R and greater than 0. Now, at this point, okay, if R is greater, if the small r is greater than the radius of the sphere, here, from this point up, we have E equals to K Q divided by R square, okay? So we must have a exponentially relation between them, parabolic, excuse me, okay? Each time you go away from the sphere, if R increases, the value of E will decrease. Here we can see the values of each point, at each point. Thank you.